Alright, so finding the derivative of a product of two functions. Alright, so you had a problem like this on your test that you just took, where you had f of x times g of x, right? And they wanted you to find the derivative of it, right? What did you do first for that particular problem? You multiplied f and g, right? And then whatever you got the derivative of it. Okay, great, that's the correct way to do it. So it says, rewrite this function as a cubic function. In order to do that, I need to multiply them, right? We're multiplying two functions, let's multiply them together and see what we get. So here we go. We're just going to rewrite it. 2x times x squared,
2x
2x cubed, 2x times negative 2x,
4x
negative 4x squared, 2x times 1, that's 2x. Alright, now let's do the other one. Negative 3 times x squared, negative 3 times negative 2, positive 6x, you can say these things here. Negative 3 times 1,
3.
negative 3, okay. Are there any like terms that I can combine?
Yes.
2x to the third minus what? 7x squared plus 8x minus? Is that the derivative or is that just still the original function, just expanded? It's still the same function, all I did was multiply it out. So then on your test, then you found the derivative, right? Okay, so find the derivative of this guy. Using the power rule, what would we end up with? Minus? Good, plus 8. Great. So that's my derivative. We found f prime. What does the equation of f prime represent again? What does this equation represent?
The slope of the tangent line at any point.
So it's an equation, right? That can be used to find the slope of a tangent line at any what? At any x value, right? For what function? For f of x, right? For the one that they originally gave us. Remember that? So it's an equation to find the slope of any tangent line at any particular point on the curve f. Alright, cool. So, back in the day there was these two cool guys. One of them was named Isaac Newton, and the other one was named Gottfried Leibniz, okay? So different people pronounce it differently, that's how I pronounce it, Leibniz. And these two guys are credited for developing the study of calculus, alright? Now, notice back when, in 1673, right, Leibniz published an article. He was bored, so he's like, you know what, I'm just going to write an article to show off to Isaac Newton what he discovered. And what he derived was what we know today as the product rule of differentiation. What does differentiation mean?
Finding the derivative.
Finding the derivative, right? The process of finding a derivative. So it's kind of like saying the product rule of derivatives, right? Okay, so what I'm going to do is I'm going to straight up tell you what he discovered. We're not going to actually try and discover it. Okay, you can do that when you get to advanced calculus in the university, where you learn how they developed all of the rules that I'm teaching. Yeah? Sounds like fun? So, the product rule is basically that. What does it mean when I say the word product? What comes to your mind? Multiplication of things, right? So whenever you have the multiplication of two functions or more, actually two functions, you would have to do the product rule. So if I want the derivative of this function h, it's very simple. What you have to do is get the derivative of the first one and multiply it with the second one. We don't touch that one. Then product multiplication goes with what? Hand in hand with what? With addition. So you put a plus sign there, and then it's going to be the first function times the derivative of the second function. Seems easy? What did they ask you on that next question on your test that you had to answer for Lillian? So some people think, well, that's what Lillian thought, right? She said, well, if I want the derivative of h, let me get the derivative of this one and the derivative of that one, and then just multiply my answers, right? Was that the same thing as what we did up on the top? No, right? Before I find the derivative, I actually need to multiply them and then get the derivative. So that was incorrect. If I wanted to go straight to the derivative from my problem, this is what I would have to follow, this particular rule. Okay? So let's say it together, right? What does it say? Derivative of the first
Derivative of the first
times the second
Times the second.
plus
plus
first times the derivative of the second.
Times derivative of the second.
Alright, so say it again. Derivative of the first times the second plus.
The first times the derivative of the second.
Alright, you have to memorize it, okay? Now, some of you might be saying, well, why in the world do I even need to know that if I could just, distribute, multiply it out, and then find the derivative? There are going to be some functions where there's nothing you can do to it. There's no way you can put it in polynomial form. So the only way to get the derivative of that function is to use the product rule. Okay? So what we're going to do is we're going to work out that same problem we just did up there, but we're going to do it now using the product rule. And then you're going to tell me which one you felt was easier, or what would you choose between the two. Okay? So let's look at it. Which one's the first function? 2x minus 3. And which one's the second function? Alright, so the cool thing about this one is when you're applying the product rule, you're already automatically getting the derivative. Okay? So I'm already labeling it as f prime. So what was the rule? What did it say? Derivative of the first. So what's the derivative of this?
2.
2 times what?
Derivative of the second.
Times the second, right? So times all of that. We don't touch it. X squared minus 2x plus 1. Plus
First.
the first, which is 2x minus 3, times
Derivative of the second.
the derivative of the second, which is 2x minus
2.
2. Are you with me?
Yes.
Derivative of the first times the second, plus the first times the derivative of the second. Okay? We're thinking of this as the first and this the second function. Alright, so let's do it. All we have to do is expand it and see if we end up with the same answer that we had up here. Okay? So let's make it look like that one. What would I end up with here? 2x squared minus 4x plus 2. Over here I got a FOIL. So that'll give me plus 4x squared, right? Minus 4x minus 6x plus 6. Are there any like terms? The 4 and the 2, that gives me what? 6x squared. The minus 4x, the minus 4x, and the minus 6x. Minus 14x. The 2 and the 6. Let's see. Did we get the same answer for the derivative as we did up there? Yes. Which one did you feel was easier?
The second.
You felt the first one was easier?
Yeah.
Okay. That's my recommendation, okay? If you're able to multiply something out and expand it and then get the derivative of it like that, that's my recommendation. If you're not, then perform the product rule. Okay? So that's what it's saying right here. Students often wonder why this rule is so important if we could just rewrite it as a polynomial and easily differentiate it. So the answer to that question is simple. If it's possible, right? So highlight that. If it's possible to rewrite, always do it. Okay? But look at this next case. It says, but in the case of this function, can we do anything to that guy? No, I have x squared times what? Times sine of x. This is the first, and this is the what? The second, is there anything I can do to that? I can't do anything, right? So I still need to be able to get the derivative of it, but I can't do anything to it. The problems that we had done before usually had a what in the middle? A plus sign, right? You would get the derivative of that one and the derivative of that one by itself, and you were good. Okay, here we can't do that. Okay, so here we need to perform the product rule. Good?
Yes.
So it says, apply the product rule to be able to find the slope of the normal line of this function when x equals pi. So what is it that we are given? The original equation. What is it that they want? Slope of the normal line. What is it that we have to find in order to find that?
Slope of the
Slope of the tangent line, right? Once I know that slope of the tangent line, I can get its opposite reciprocal and I'm good, right? Okay. How do I find the slope of a tangent line? I have to find the derivative. Awesome. Okay, so let's find the derivative of this guy. And we're going to get the derivative automatically just by using the product rule. So what's the first? Derivative of the first, 2x times the second, sine of x, plus the first times the derivative of the second. What's the derivative of sine? Cosine. Awesome, we're done. Oh, that was so hard. Okay? Yes or no? Good? Could we do anything to it to rewrite it? Do we have to do anything? No, not all the time, right? Unless it's multiple choice and you want to make the answer look like the multiple choice, right? Or unless they tell you the derivative is this, show me how to make the answer, or show me that this is the derivative, like on your test, right? Okay? So, for our sake, we don't need to, because all we really need to do is evaluate the derivative at what? At pi, and that's going to give us our what? Our slope of the tangent line, and we can use that to find what we ultimately want, which is the slope of the normal line. So plug in the pi. So we have 2 times pi times sine of pi plus pi squared times cosine of pi. What's sine of pi? 0. So 0 times anything is what? 0 plus, what's pi squared? Pi squared. What's cosine of pi?
1.
Negative 1. So what do we ultimately end up with here? Negative pi squared. So that's the slope of the tangent line. What would the slope of the normal line be? 1 over pi squared. Very good. It's negative here, so we need the opposite, so positive, and we need the reciprocal, right? Good? Good. We're going to be doing a couple of abstract things today, so you're going to have to change the way you think, all right? So for example, that one, you're not going to freak out because you saw pi numbers. Keep working for this, okay? Good? All right. Let's try some more examples. And I'm going to let you decide what you want to do. For example, this first one, what do you want to do? You want to expand it first?
Yeah.
All right, go ahead and expand it. Thank you, sir. Wow.
Yeah.
All right, so what do you think? What did you decide on this one? Expand it?
Yeah.
All right, so 2x squared times x squared, what do we end up with? 2x to the fourth. 2x squared times negative 3. 3x times x squared. And 3x times negative 3 minus 9x, okay? So notice that here, we're not finding the derivative right now, we're just rewriting the original function, right? So now we can find the derivative, and let's do it in order. So we'll do it with the highest degree here. So what would that give me? 8x cubed, then we'll do the cubic part. So 3 times 3 is what? 9x squared, then we'll do the quadratic, minus 12x, and then we'll do the linear, minus 9. That was easy? Did any of you do the product rule on that one? No?
No.
Okay. How about the next one? What would you want to do there? You want to just expand it? Okay. So this guy right here becomes what? X to the half, right? Okay, so what do I do when I multiply with the exponents if they have the same base? You add them, right? So this times this times this, and this times this. So we're gonna end up with what? X to the what? 5 over 2 minus 3x to the, what's 1 plus half? 3 over 2 plus 2 to the, or 2 times x